This Zoom session is being brought to you by the Fractal Horizon. Okay, for today, through to next Monday, we will be doing 2 sections a day, and then after that, 1 section a day. Today, 2.1 and 2.2. 2.1 is about angles and their measures, and 2.2, we finally actually define the trigonometric functions. I find that generally in math courses, it takes till covering the 2nd chapter before we actually get to the material mentioned in the title of the course. All right, now, angles. Okay, an angle is 2 half lines with a common vertex here. There's one called the terminal side, the initial side, and one called the terminal side. You have envision as a rotation from initial to terminal side. If the rotation is counterclockwise like this, then it's counted as a positive angle. If it was when the other way clockwise like this, the angle will be considered negative. All right, now there are various types of angles depending on how big they are. Here, an angle like this between 0 and 90 degrees is called an acute angle because of the sharp point here. 90-degree angle makes or the square, making a square is called a right angle. A little bit beyond a right angle, between a right angle and straight, is called an obtuse angle because this corner here is dull, I suppose. If it's 180 degrees, complete reversal of motion, that's called a straight angle. Now these next few are names I've made up myself because I think they need names. When it's going beyond 180 degrees, but not quite 270, it's what I call a breakback angle. If here it's between 270 and 360 degrees, I call this a Pac-Man angle because of the video game, and I've just dated myself. If it's one full rotation around, that is denoted a 360 degree. It's 360, it's called a rotation. And you might go around several times and get angles beyond that. Standard position of an angle puts the initial side as the positive x-axis. And that way we can draw this diagram, this sort of circular protractor denoting various angles. So this will be 0 degrees, and it's also the same as 360 degrees around. We have angles 15, 30, 45, 60, 75, 90, 105, 120, 135, 150, 165, 180, 195, 210, 225, 240, 255, 270, 285, 300, 315, 330, and 345, and like I say, one full 360. A rotation is 360 degrees. A degree, hold on, Yoshiharu, excuse me while I make a note here. 1 degree is 1/60th of a 1/360th of a rotation. It's also denoted as also 60 minutes, denoted by a 60 slash mark. And 1 minute, very tiny angle, is made of 60 seconds. A second is an even tinier angle, 60 double dash seconds. So there's this thing called degree minute seconds notation. Very ancient notation. By the way, the reason why it's 360 degrees in a circle, sort of arbitrary actually. There's something called an engineer's notation where it's 400 gradients, I think they call it in a circle. 360, well, it goes all the way back to the Babylonians. And they did it because they wanted to do astronomy, astrology really. And 360 is a highly divisible number, divided by 2, 3, 4, 5, 6, 8, and 9. That's pretty good, and 10, and 12. So that's pretty highly divisible. And it's close to the 365.25 days in a year, average year. So they settled on that. And talk about tradition, a tradition going back to the Babylonians. Amazing. Anyhow, so degrees, minutes, seconds, DMS. D degrees, M minutes, S seconds. Well, it's D degrees. M minutes, well, it's M over 60th of a degree. And S seconds is S over 3600ths of a degree. So for example, 40 degrees, 10 minutes, 25 seconds is how many degrees? 40 plus 10 60ths. So it's 25 over 3600. And if you work it out, it's 40.17361111, repeating forever, degrees. 9 degrees, 9 minutes, 9 seconds. 9 minutes plus 9 60ths of a minute, of a degree. 9 degrees plus 9 60ths of a degree plus 9 over 3600ths of a degree comes out to 9.1525 degrees. Now, if we had decimal degrees, which is what we do nowadays, I want to convert to DMS, well, you sort of go reverse. 40.32 degrees is what DMS. Well, it's 40 degrees plus 0.32 degrees. Now, okay, to find out how many degrees that is, you multiply it by 60, so it's 19.2 minutes. All right, so it's 40 degrees, 19 minutes plus 0.2 minutes. Multiply that 0.2 times 60 to get the seconds. So it's 40 degrees, 19 minutes, 12 seconds. Or let's try this. 18.255 degrees is what? Well, it's 18 degrees plus 0.255 degrees. This 0.255 we multiply by 60 and find that it's 18 degrees plus 15.3 minutes. So 18 degrees, 15 minutes plus 0.3 minutes. Multiply 0.3 minutes by minutes to get seconds. You get 18 degrees, 15 minutes, 18 seconds. So here we converted from DMS to decimal, and here we converted from decimal degrees to DMS. I think your calculator might have such a utility on it. That depends. Now, I mentioned that it's 360 degrees in a circle, and that's entirely arbitrary because they wanted to have something highly divisible and also close to the number of days in a year. Basically astrological reasons. Well, around about 19th century or 18th, so some of the mathematicians wanted a more natural thing. It doesn't have to do with conventions or culture. They wanted something having to do with the actual degrees on the page, the angle on the page. So here's what we do. One full rotation will denote as 2 pi radians. The radian is basically talks about how far around the circle in distance it goes. Here's the idea. If you have a circle with radius r and an angle theta measured in radians, and this length s, arc length s, then we'll say that s equals r times theta, where theta is radians. Or in other words, theta is s divided by r. The radius of the circle divided by the arc length is the degrees, is the measure in radians. Therefore, if you go around one full rotation, radius r would be 2 pi r around, so 2 pi r over r is 2 pi, therefore 2 pi radians in one full rotation. 360 degrees equals 2 pi radians. So 180 degrees equals pi radians, or we'll have what we call our unit conversion factors. Pi radians divided by 180 degrees equals 1. Conversely, 180 degrees divided by pi radians also equals 1. And since you can multiply anything by 1 and it stays the same thing with this. So you have something in degrees, you multiply by pi over 180. Degrees will cancel and you get the units in radians. If you have something in radians, you multiply by 180 degrees over pi radians. The radians will cancel and you get an answer in degrees. For example, 45 degrees. Well, we'll multiply 45 degrees by this, pi radians every 180 degrees. We do it multiply by this because that way the degree units cancel. So you get 45 pi over 180 or pi over 4 radians. Or conversely, 0.5 radians. How many degrees is that? Well, 0.5 radians times 180 degrees for every pi radians. We choose this or this depending upon which we want to cancel out. Here the radians is in the denominator and it cancels these radians here. So you get 0.5 times 180 over pi degrees. So 90 over pi degrees, which is about 28.65 degrees, approximately. Now, okay, we can do a little bit more measuring of the circle in terms of its area, for example. So we have a circle. This is a radius r, an angle theta measured in radians. That's important. And A is the area of this sector. Then that sector's area is 1/2 r squared theta. For example, if the radius is 0.75 meters and the angle is 15 degrees, what's S and what's A? What's the arc length out here? What's A, the area in here? Well, first we have to convert 15 degrees to radians. 15 degrees, you multiply by pi radians for every 180 degrees. degrees in the denominator, so this degree and this degree cancels. 15 pi over 180, that's pi over 12. So the angle is pi over 12 radians. So S equals r theta. R is 0.75. Theta in radians is pi 12ths, and the units are meters. And you multiply it out, it gets pi over 16th meters, or about 0.1963 meters. The area is 1/2 pi r, 1/2 r squared theta, excuse me, 1/2 r squared theta. 1/2 r squared is 0.75 meters squared. Theta is pi over 12. And okay, you multiply it out, 3 pi over 128 square meters, approximately 0.07363 square meters. And okay, we have examples, a couple of examples from the book. 7 pi over 12 radians is what? Well, we multiply by degrees per radian, so the radians cancel. 180 degrees divided by pi radians. Radians cancels, pi cancels. 7 times 180 over 12 is 105. So the angle is 105 degrees. Negative 40 degrees, that's a clockwise turn. How many radians? Well, negative 40 degrees. And then we'll multiply by radians per degree. That's pi radians for 180 degrees. The degrees cancel. Negative 40 pi over 180 comes out to negative 0.69813 radians, approximately. You have an angle of 42 degrees, a radius of 17 centimeters. What's S, the arc length here? What's A, the area of this triangle-ish sector here? Okay, first we find the angle. 42 degrees multiplied by pi radians for every 180 degrees. So the degrees cancel. You get about 0.733038 radians is the angle. S equals r theta. R is 17 centimeters. Theta is this, 0.733038 radians. Multiply it out, you get, to 3 decimals, because that's really all it's justified. 12.5 centimeters. A is 1/2 r squared theta. 1/2 times 17 centimeters squared times 0.733038, approximately 105.9 square centimeters. In both of these, I took these out to 1/10 of a unit accuracy. And that's about all it's justified, maybe even a little more. The idea being that these are only accurate to units. So going down to tenths of units is already pushing it a bit. And beyond that, it's more than necessary or really justifiable. Okay, there's that for that. Let's stop this. Oops. Stop this.